Okay, let's start class. Okay, I'm gonna review, actually, not last week, right? Lecture we had 2 weeks ago. Then some of the remainders actually in chapter 2. Then I'm going to introduce vector space and subspace. Also, we might be able to cover column space as well. Then tomorrow I'm gonna discuss about solving this AX equals 0. So 2 weeks ago we discussed about Gauss elimination in matrix form, right? So everybody understand that, right? In high school you already learned Gauss elimination. So only thing we did was we just computed this Gauss elimination using matrix. So Gauss elimination is steps of fourth elimination, right? Using row operation. So sometimes we will fail. So fail means when you have 0 in pivot, then you have some failures. In case you can switch the row to solve the problem, then we can continue after row exchange. Otherwise, we are going to fail. Then once you have a triangular matrix, then you are able to solve the problem by using backward substitution. Okay? So when you solve this solution, there is 3 cases. First case, you have one unique solution. Another case, actually, you don't have any no solution. Last one is actually you have many, infinitely many solutions. Okay, also we discussed about representing this row operation using matrix, like elementary matrix and permutation matrix. Okay, so you just remember some of these cases. Anybody has any questions on the lecture we had 2 weeks ago? Then also we discussed about inverse matrix, right? So also we learned about how to derive or compute inverse matrix using Gauss-Jordan method, right? So I'm going to skip that. Also, we learned about LU factorization. So 현상 1, why do we do LU factorization? So we learned about how to do factorizing matrix A into LU, like lower triangular and upper triangular, right? So why we did that? Or simply for fun or what? So anybody else can give me some answer? Kim Jong-hyun, why did we do LU factorization? Okay, bottom part of this, okay, EA equals U. That's the one we are using Gauss-Jordan. Actually, using Gauss elimination, you are able to transform matrix A into upper triangular, right? That all the operations are represented using elementary matrix, right? This is the one we solved, right? Oh, not this. Let's try to, okay, this is AXB. What about this B, right? in case we have only one set, like P1, then we can solve this problem using Gauss elimination, right? Like the first Gauss elimination actually is convert A to what? AX is B. We convert this problem to, using Gauss elimination, then it becomes, Ux equals C, right? Once you have like this upper triangular matrix, for example, it's all 0 here, this X, whatever values of C, now we can solve a problem here. By using that value, you can substitute here, then you can solve the value of this one, right? If you can use these both values, then you can solve this problem, right? So the process of transforming A to U is triangularization using Gauss elimination. So getting values of X this way, this is backward substitution, right? So we can solve the problem for one by one, right? What happens when we try to solve the problem, this problem for, let's say, assuming we have 5 set of B. So 박한솔, how can you solve the problem? We just applied it 5 times, right? Right? Just using the same method, you can apply it 5 times, right? I'm saying, okay, we solve the problem. Let's say basically we solve the problem once. AX is B1. Actually solve one, AX B2. This is another solution. Then you can solve AX is B5. We can solve the problem 5 times, right? Then 정민영, how much computation do you have to carry out to solve this problem? Assuming A is m by m matrix. A is m by m matrix. It's n rows and n columns. It's how many multiplications or how many divisions, how many additions. So we did that, right? Around we have to have like triangularization. We need for row operation. We need a cube, right? Why? That's something we did, right? Like when you have this one row, then take a pivot here, right? We have to try to make 0 for all these, right? Right? In order to make 0 for these, let's say, what operation we do here is actually, basically, operation is subtract whatever. Let's say, let's say 3 times row 1 from row 2. In case this value is 1, this value is 3, right? So in order to have this operation, how many multiplication do you have? Any idea how many multiplication do you have? 2? Because we have all these n elements here, right? So basically, we multiply all these n elements, then we multiply them as just ignore subtract. Just multiplication in this case, n minus 1 multiplication, right? We have to multiply whatever 3 to each of these coefficient. They have to subtract from this, right? Oh, just ignore the first one. This because n. Then this is like in the case of this 10 element, right? Then first one is multiples. Then this you don't have to compute this one. Always 0, right? Yes, obviously you need some division. So in that case, you can say, oh, just n multiplication up. Then we have n minus rows here, right? So basically, we need at least n minus 1 square multiplication, right? Then next one that we have to reduce also this one again, like 0, 0, 0. Then this n minus 2 square. Then another one is whatever this go down, then 1 square. Then when you add them up, is computational is around n cube, or you may say n minus 1 cube, or doesn't matter actually, it's 3. This total number of multiplication you have to carry out. So when you try to solve 5 set of problem, each one you have to do it again and again and again, right? So rather than doing that, actually we have some kind of LU factorization. In this case is when you try to solve the n set of equations, then once you have some LU factorization just once, which is computational complexity is n cube, then you can solve 2 sets of problems. Let's say you try to solve AX. No. It's B1. So you try to solve AX B5. Right? Is one way to solve the problem is once you factorize, then is once you have factorized A to LU factorize, right? B, right? Let's think about it. This is lower triangular matrix. 박한솔, how many operations how many multiplications do we need to solve this problem? Let's say I'm asking you like Gaussian elimination need around complexity of the n cubed by 3 multiplication. Then solving the problem like let's say we know what this U, X is C. This is upper triangular matrix. It's all 0, all X, whatever this value of C. To solve that problem, what's the complexity? In this case, we have value of this easily, right? Then substitute this value, then you can solve this problem, right? Then substitute this value, then you can solve the problem pretty easily, right? Then all this multiplication actually is not that much. So how many multiplication? When you apply here, then probably I'm claiming multiplication is at the most n squared by, yeah. 예? 아무것도 안 보여? I'm asking, like when this is backward substitution, right? I asking you what's the computation, the complexity. This one actually is because you are substituting value one by one. Then we say okay, because multiplication only occurs when you like, for example, like 3x for 3 times 2, then you just add values, then you compute that. So actually, its multiplication is probably at the most is like n squared divided by 2. Just ignoring this, actually, the solution here actually it takes when size n becomes large, so computational complexity proportional to n squared, right? Have you learned about the computational complexity in programming class? No? How come? Have you learned any sorting algorithms there? Any sorting algorithms? 김명진? In 입소설 class? Have you learned about linear sorting? Let's think about it, okay. Here's what I try to deliver to you is, okay, you write one program for sorting whatever this array, okay. 현상 one use another program which sorts this array. Now, then I says, how does it take to run your program? Is it important? How long it takes? Okay, so basically, time to execute program is very critical issue, right? Then time to sort the list depend on how many items in the list, right? So you may say, let's have searching, not sorting. Assuming you have n element. You see, n might be 10 or 1,000 or million or billion or whatever, right? What's the fastest method to search that? You can check slowest one, you can check one by one, right? Then searching time proportional to n, right? Are you satisfied is fast enough or might be too slow? When n is 1,000, it's okay. Like when you address book, you try search all the entries one by one, try to find your friend 현상은, no problem. Just search one by one. Just 1,000 entries, no problem, right? In case it's 1 million entries, what are you going to do? You're going to search one by one for all 1 million entries? It can take some time, right? So Wonjun, so what's the better method?
Making
tree.
Yeah.
That's one way. Sorted, right? Binary tree, right? Yeah. In that case, how long does it take? What's the complexity? When you make a tree, you need binary tree, right? Then what's the height of this tree? When you have n element. Log n, right? Then another one is log n, right? So program might be a little bit more complicated, but for large n, this might be much faster, right? What's the another one? Have you learned hashing? another which is called hashing. This might be just constant. Can you think about what's the method of constant might be? Let's assume, let's say, we have like 100 friends. You are storing phone numbers in your database, okay? Then somebody called you. They search database. If they find somebody there, they'll display their person's name, right? That's what your address phone does, right? Nobody there, then they will display their phone number, right? This is caller ID, right? Like caller ID program. So they just search database. If that person appears, they'll try to find out whether it has pictures, right? Photos, right? If the picture is there, then they will display picture and name, right? No picture, then they display name. 이영경. There's nothing there, then they will display what? Phone number, right? So in that case, the time to find the entry is very, very critical. So one way you can search using binary tree, right? So using that, you'll take log n, right? What's another method? Take hashing. Basically, let's say, oh, I'll come up with 1,000, let's see, this pen is bad. I may come up with 1,000 boxes. Box. Then you have a phone number here. Let's say my phone number is. I says, okay, I just use this 3 digit. Okay. Then okay, I'm gonna put this one is this bin 370. Okay, Myungjin, what's your phone number? Last 3 digit. Then you may say store here. When you have like only 100 entries, most of them are just when you go there, only one item. Sometimes we have duplicate, right? 2 entries might be there, right? So when somebody called it, the base of that take the last 3 digit, try to find the box. If box is empty, okay, it's not there. So only one entry, then actually go there compare with whatever numbers, right? 2 entries you can search there. It's much faster in that case, right? So actually when you do this factorization, actually you have to think about it. Why we do this? Basically, this operation is much cheaper. These are much cheaper. This one is actually multiplication is proportional to number of dimension, array size, matrix size. This one is proportional to n cube. Like when n is small, it doesn't matter that much. But if n is 1,000, it makes big difference, right? Here is we have around 1 billion operation, right? Here is what? N cube. 1 billion operation, right? So that's why we just converting their problem rather than solving their problem, just transform their problem another way. By doing that, you may have some more steps, but eventually you're going to have less computational complexity. Okay, so and then transpose, and this one I'm going to skip it actually. You can just read it. You know what the transpose is, 전치, right? With matrix, right? So I don't have to explain that. Just read it. Today actually I'm going to spend time on vector space. Probably in high school, you learned a term like this one. What is R cube? Have you seen such a letter in high school mathematics? I have 수학의 정석. I saw some such a I have a copy of 수학의 정석, the high school math 참고서. This three-dimensional, right? This x and y in g, right? This is a three-dimensional axis, right? Then you can say, okay, this all the point here is actually tuples of three letters, right? Okay, this is basically A and B and C, right? So A can have any values, B can have any values, C can have any values, right? This one is, I says, okay, this is three-dimensional space. 3차원 공간? That's what you learned, right? What's this? Right? 2D space, right? Then 2D space is this, right? Then this is R1 is 1D space, right? When I say, what's the G3? What's the G? Is complex numbers? Yeah, complex numbers, right? Three-dimensional complex. Instead of real complex, right? I say, oh, no, I say now mine is N2. What is N? N2 is more or less, this is natural numbers, right? So you know what the spaces are, right? Right? So all spaces, because this three-dimensional space, two-dimensional space. Most cases we are dealing with real numbers, but some cases we are dealing with others as well. Basically, Rn is actually is n-dimensional space. Might be one-dimensional or 99-dimensional. Who knows? Maybe so many dimensions. Let's say assume this. You have everybody has a camera, right, on your phone. So how many pixels do you have on your camera? 4 million, right? Let's say 4 million. 4 million pixels. So each pixel, how can you represent each pixel? Each pixel, do you have any idea? Each pixel, how many actually bit or whatever? Whatever. Each pixel usually consists of RGB, right? Red, green, black, right? So each red and green usually represents 8 bit. 24 bit, right? It's 24 bit, right? So here is actually each pixel is represented as a binary number, right? Whose size is 24 bit, right? Then I can represent whatever I say. Okay, I'll define this I. I is basically I'm defining 24 bit. Number, right? Then what's this one is, oh, I said this is 4 million dimension, right? This is space, right? It's a whole of the pictures I can describe as dimension is 4 million, which is very large. Then sometimes you can compute, then you can compute this problem. Usually think, okay, no, we don't need the dimension, but reality, actually we have sometimes very, very huge dimension. Okay, so here actually those R might be here is basically, we always say all the tuples. In that case, actually we can say maybe integer, sometimes real, or sometimes you may say rational numbers, sometimes prime numbers. So it might be most cases it's real. Then here actually I try to explain with another one. So some of this is a review of the high school mathematics. Have you learned about the closure or 닫혀 있다? Can you explain what it means? 닫혀 있다?
Set has a closure under an operation if the performance of that operation.
I don't need that. Just explain what you understand. It's okay to you can explain in Korea.
결과가 그 집합 안에 들어있으면 닫혀 있다.
In order to describe closure, first of all, you have to describe set first, right? Whatever set, right? Set, okay? Then also we have defined what? Operation, right? Right? When you apply whatever operation to a set, the result also belongs to set. That's a closure, we say. Sometimes when you apply operation to any element on the set, the result might not belong to the set. In the case, this is open. Okay? Let's think about this, like positive integers. So 1, 2, 3, right? It's closed on the plus, right? Operation, right? When you add up, it's always positive integers, right? How about the minus? No, you get 5 minus 10, that's minus 5. It doesn't belong to there, right? So we're closed on the multiplication. Even division, we don't know what the real division means. Even not real integer anymore, right? It's fractional numbers, right? So you can apply these things. Like for the all integers, right? In that case, closed on the plus, closed on the minus. It's so closed here. Don't know. It all depends on how you define division. Actually, division is not well defined there, right? Even result might not be integer at all, right? If you define it as a mode, that might be different, right? So now you have concept of set operation closure, right? Then now I try to explain what the vector space is. They actually often we use like a field like set of integers. Now we talk about like set of vectors. Instead of a set of integers or set of reals, now set of vectors. Okay. Then what kind of operations do we have on vector? Okay, here we define, we do not define all of them, okay? We just define add. Add in a way, add, right? Add actually is like when you vector v1 and v2. If whatever this set is closed, it means if there's a closed, then v1 plus v2 has to belong to the space, right? Then another one is multiplication. Actually, multiplication, not between vectors, actually, multiplication of vector by scalar. Then actually CV. Or this also has to belong to the space if they are closed. Okay? So basically, if they satisfy these, then that's a space we call vector space, which are closed. Okay? Method operation actually is addition. When in 2 dimension, we can explain easily. Like when your operation here is x, y, then we know how to v1 This V2, how to add them, right? This is add, right? This is V1 plus V2, right? This is addition, right? Then what's the multiplication? Like when you have V1, then it's with 2V1, you have two sides, right? Minus V1 is minus side. So because if we allow minus values for the C, we don't have to define subtract, right? So addition is enough, right? So that's what we call vector space. So in that case, we say, okay, when you have V1, V2, actually, this is equivalent to CV plus DW. Actually, any linear combination of vectors, this actually is equivalent to this representation. So when you have any two vectors, pick any two vectors, by combining them linearly, whatever result one here, also that has to be in the same space. Then we call that as a vector space. Okay? Let's assume this is whatever the quarter space. This is a vector space or not? This is not closed on the linear combination, right? When you combine, why? Because we allow minus in this multiplication, right? If C is we allow plus, it's okay, right? Problem is we allow minus, right? How about this one? This line here. This line, is it closed or not? Can you explain why you say it's closed? Okay. I say it's not closed, actually. Why? Here's this line, right? Let's say this is a special point here, right? Any vector here, right? This is one vector, right? Let's say this is V, right? I say, then any combination, then okay. I say the CV also has to belong to the line, right? How about C is 0? The 0 times B, right? Then this origin, right? It doesn't lie on the space, right? So for the line to be a closed vector space, it has to pass origin. Otherwise, it's not, right? So I can say this second line, which is passing the origin point, yes, it's closed. Kim, how about this? What about this marked area? Is it closed vector space or not? It's not, right? When you combine them, whatever scaling up, then it just fall outside of a circle, right? Just be clear, you understand what really means, like set whatever the whole space, then what operation we are talking about, then whether we are closed or not. So only operation we are interested in this linear algebra is a linear combination. So addition of two vectors or multiplying vector by scalar coefficient. Okay? Yes. Oh, this one? Okay, here is what I'm saying here is
근데 원에서도 그 똑같이 산수를 곱해주면 다 지나지 않아요? 오리진을?
no. Here is what I'm saying. If pick any point here, right? You can have some multiply whatever this vector by C. Okay, this is vector V, right? It's okay. I'm gonna apply this C, V. Whatever this will come up with another vector, right? It has to lie on this line for any value of C, right? Yes, okay, then I'll say, okay, assume C is 0. Then this becomes 0, right? Well, test should be origin, right? Which is not on the line. Right. Like any combination, basically this is set. Okay, this is operation. Okay, we define two vector operation addition. Pick any vector here, V and W. Then when I add them, they have to belong to here. Or I say any vector is V, I just multiply by whatever coefficient, that they have to be belong to here. So that's a condition. That's the way we can say it is closed. Okay? In this case, when I pick V, they multiply by 0. That's outside of the plane. Okay? So another one is subspace. Subspace is basically vector space within a vector space. Let's think about two-dimensional space. R2. You can represent R2 as this one, right? X, Y, Z, right? R2 is a whole space, right? It's infinite, right? It's whole space R2. Is it closed? Right? Then how about the line here? Any line. It's closed, right? Basically, when you scale it up, actually, when you pick vector here, this one, okay, basically it's scaling, right? Or adding this one is another one that still is same on the line, right? How about just nothing else? Just only thing I have is just this origin point, 0, 0. Also when you add them up, it's always 0, right? Multiply by any number, still is 0, right? Okay, so in that case, we have three possibilities: all spaces, or any lines passing that, or just origin point, right? So in the case of three-dimensional space, so what surfaces are possible? One is whole space, right? The other one is plane, which include origin point. Or other is line, include origin point, or just origin point only. Okay? Like in the case of space, of three-dimensional space, it's a plane. Is whatever this, plane which pass the origin point or line. This is both are subspace, right? When you join this operation by union, is this one also subspace or not? 유형우. This is subspace or not? Not. How about this? Subspace. You guessed well. Okay, I don't have to explain these things. Okay, think about it. So, are you clear? on what the spaces are, what's the vector space enclosed, also what's the subspace. Okay? Then we have better understanding once we discuss about solving their problem tomorrow. Then you say, oh, that's why we discuss this vector space or subspaces. Okay? Today, just the only thing is I say is space and space. 현상원, what's the column vector here? This is one column vector, is another column vector, right? As you see, this is a matrix, right? This is matrix, right? One way to view this one. Oh, this is a collection of two vectors. So vector 1 and vector 2. That's the one way to view it, right? Vector 1 is 1 to 4. Vector Vector 2 is, this is 1 or, okay. Vector 1 is 1 to 4, vector 2 is 3, 1, right? Kim Myung-ji, do you remember we discussed about column space? Column space. Let's say we said, oh, that's the one with the three dimension. So V1 is column vector 1 to 4. Then V2 is 3, 3, 1. So 1 to 4 is okay. This x, y, g. So 1, 2, 3, 4. Whatever those. One is somehow like this. This V1. Okay, V2 is 3. Whatever 3, 1. I don't know how to represent it. Somehow. Somehow these two. Then this is a way, okay, V1 and V2, this is called this column space. Then we can represent this as two vectors. Then this V1 and V2, right? Can you come up with the spaces which include this V1 and V2? Let's discuss about that. Okay, probably I may misuse the terms. We don't have row picture and column picture, right? Do you remember that? When you two equations, I said so one is one, I can represent these two lines across, then this is row 1, this is row 2, they are represented as an equation, then they meet, there's solution, right? That's the one we discussed, right? The other one is actually we discussed was, okay, let's so it's like 2x plus right? One way is to see the two lines. So the other one is actually 2, 3 as a one matrix, this 1, 2 matrix, then 2, 3. 2, 3. This vector 1, 3, 2. So 2, 3 is vector 1, the 3, 2 is vector 1 actually. That's the way we can also represent. Then combination in a way is, okay, now scaling vector 1 by x, then scaling by vector 2 y, then we can add up, then this is the result matrix. Okay, anyway, so can you think as A as a combination of two vectors? Let's say when you have this, whatever this matrix A, I can say, okay, this is V1, and this is V2, this is Vn. Can you think of what this as a collection of matrix, a collection of vectors? We can go back to all the pictures, but let's think about this way. Let's look at this, 3x1 plus 2x2, okay? Let's also 5. So how do I represent this as a matrix? This is matrix, okay, 3, 2, 4, 1. This x1, x2, right? Then 3, 5, right? This is matrix representation, right? Can I rewrite them in a way, let's say, oh, this 3 times 4, I say this x1 plus can you write this way? 이형우? This is just we are using matrix, right? Here we are using vectors, right? Oh, this is in a way, oh, this is a linear combination of two vectors, right? Right? This is the first vector, the scaling up using x1. The second vector, scaling up using x2. When you add them, oh, this becomes 3, 5. This is another view on the same subject, right? So this is one we call column vector. Now you can understand it? Okay? So you can see this one actually, when you array, whatever A, I can, oh, A is all this V1, V2, okay, Vm. You can see as collection of those vectors. Then you can, oh, this is x1 to x3. Oh, this one actually is added just, oh, I can say this is actually just a linear combination of V1, coefficient also x1, V2, x2. So you can represent it this way, right? You can dot, 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 you can have many of them, right? That's, oh, this is linear combination of vectors. That's why we call this one as column vectors. Okay? So when you have 1, 2, 4, 3, 3, 1, when you combine them, right? Basically, I say this is a three-dimensional space. X and Y and G. So we have two vectors dependent, 1, 2, 4, 3, 3, 1. Then I can combine two vectors in linear combination. The same as this. So this is matrix form. This is more vector form, right? When you do this, then we can say we can have any value of x and y. Does it fill whole space or does not fill whole space? 박한솔. When you can have, basically we have two vectors, right? We linear combine them for any values of x, y, and y, right? In that case, does it fill whole space? I'm saying, does it cover whole this R cube? Why? Linear combination of two vectors only spans plane, right? Right? So it only covers right? If you have only one of them, then it covers only one line, right? Two, then we have only covers plane, right? So when you have two of them, actually, whatever linear combination we have, we only covers one plane. Other areas are not touchable. Okay? Let's assume, okay, now we have all this plane here. Okay? Just think about it. Now I said, okay, this column vector, whatever V1, whatever V2, then okay, it covers all the spaces here. Okay? Then I say there is, okay, whatever x1, v1, x2, v2 is v vector. Whatever this, let's say, assume this one, 2. Does it have solution? On what condition do we have solution? Let's say it is 1, 2, 3, right? In this case. If that vector is on this plane, then we can find the solution. If the vector is not on the plane, it's not a solution. Because we try to combine these two vectors, whatever values of x, y, a, then only covers this area. Then I said, my addition is somewhere else. Then no way to find solution, conceptually. Hakojin, can you understand it? Okay, this is another matrix, right? This is 4 by 3 matrix, right? So we have 3 column vectors, right? First column vector is 1, 2, 3, 4. Second is 1, 1, 1, 1. Third one is 2, 3, 4, 5. Then what's the column space? R4 or what? What's the dimension of the subspace? I claim is plane because this is a linear combination of two. I'm saying they are not independent. Let's assume that these things. Just think about a very simple example. Because two-dimensional is much easier to see. So 1, 1, 2, 2. Okay? Then here is x1, x2. This one I can say 1, 1, x1 times 2, 2, x2, right? Right? Does it cover whole plane or just what? Line. Why? Right. This one, in a way, I can say 1, 1, x1 plus 2x2, right? With this straight line, right? So in this case, it's does not cover. Let's assume this is okay value. Then I say, okay, 2, 5. Do I have solution? 이현경, do I have solution here? No, because it has to be on this line, right? Then if I say it's 5 by 5 by 5, it has solution, right? Right? Even in the case, actually, how many solutions do you have? Will you have only one, or do we have so many solutions? In this case, actually, it's x1 plus 2x2 is 5, right? We have so many solutions, right? It's more than one, right? Basically, we try to learn all these things because up to now, we discussed only when there is only one unique solution, there's not much problem. Sometimes we have so many solutions, we try to find out all those solutions. That's why we are adventuring this one. Okay, this is, I say, is a column space. In this case, actually, because these are linearly dependent, because by combining these two vectors linearly, we can come up with this. We call this independent. Because V1 plus V2 actually becomes V3, right? So it doesn't help. Even here, like, oh, here's this one, this is just by multiplying 2, it's dependent, right? So actually, it's not two-dimensional. This one actually is not useful when you come up with space, right? So that's the concept we have here. Okay, this is a question we have here. The same matrix, right? A. Then x1, 2, x2, x3, then b1, b2, b3, b4. Here is 4 equations, 3 unknowns. Does it have a solution all the times, or what condition should be satisfied to solve the problem? This is, in a way, is very, in a way, tricky problem. You always solve the problem. Okay, n unknowns. Then equation is n equations, right? That's the problem you always try to solve that, right? How about in this case actually is, oh, no, I'm not. I'm case is, this is 4 equations and 3 unknowns. Very strange, right? What's your first impression? Do you have any solution for this problem? Or in high school, mostly, oh, number of unknowns should be same as number of equations, right? If that's the case, oh, 3 unknowns, 4 equations. Oh, this shouldn't be. There's no solution. That's the probably case you have, right? Because, okay, I can solve a problem, 3 unknowns and 3 equations, but there's one more constraint I have to satisfy. So I couldn't find any solution, right? How causing, right? That's the probably logic may go, right? But they may not be the case, all depend on what kind of equation, right? Sometimes you may say, oh, I say 4 equations, but I may have 5 unknowns. Then I say, what are you talking about? Do you have this case? Do you have to solve this problem? Oh, you don't have to? Let's think about this. Two unknowns and 4 equations. Do you have to worry about those issues? 유영욱, do you have to worry about these issues or not? I think some of the topics here actually is, let's say, we have one of the example was, okay, this level, whatever this weight, then we try to come up with some solution here, right? Then I say, okay, we have whatever this x, y, whatever this known, whatever this distance, whatever, then okay, we have like 2x plus 3y, 10, or whatever 3x plus 10y, whatever, 50, right? But let's assume we try to come up with some measurement. Then, oh, I have another, I just measured, I just do a little bit differently, right? In reality, when you come up with the equation, right? Oh, I measured that. Right? Because you try to come up with some modeling, right? You may have more than 2 equations, right? So what are you going to do? You just pick whatever 2 of them to solve them, or what are you going to do? Actually, this is a different problem. Actually, because only this says, okay, this line 2, I know this is only one line, right? Okay, sometimes I have the measurement here. Line here, line is only 4 of them. I like to draw one line, which is best solution. It's okay, best solution seems to be like this. Right? But this is a measurement error, right? This might be, you can say this is approximate solution which have best for this, right? We call that as a linear estimation. Okay? This might be better than just pick any 2 equations and solve them. Like from this example, let's say this is a 4-dimensional vector space, right? And the 4-dimensional column vectors, right? This 1, 2, 3. So what's the column space for this matrix A? Because we picked these are dependent, right? So column space of A is 2-dimensional, right? So it's plane, right? If B1, B2, B3, B4 are on the plane, then we can solve them. They are not on the plane, sorry, we are not able to solve them. So can you understand that? Because basically we have 3 vectors. This x1, x2, x3, that's a combination. So taking whatever values, x1, x2, x3, whatever combination, then they will reside on the column space. Okay? If whatever b vector are not on the column space, I'm sorry. Whatever combination I have, still I cannot reproduce that vector. Okay? So that's the basic concept. So here actually, there's some solution here actually. So I can solve the problem when you have all 0, right? So actually previous example, let's say all b's are 0. What's the solution for x of 1, 2, 3? 0, 0, 0, right? Then what's another one? Let's say the 1, 2, 3, 4. Then what's the solution? Yes, it is 1, 2, 3, 4. 1, 0, 0, right? So these are only solvable when P is in column space. So basically, in this case, actually, this one also is not that meaningful at all. Okay? So when you make, let's see, this A, right? And you try to make triangular. Okay, can you try to make a triangular? 1, 1, 2, 2, 1, 3, 3, 1, 4, 4, 1, 5. Can you make a factorization elimination? Then this 1, 1, 2, then 0. This is minus 1, right? This minus 1. Then here is 0, minus 2, 3, minus 2, then it's 0, so this is minus 3, right? Then when you go one step further, what do you have here? 1, 1, 2, 0, minus 1, minus 1. Right? So in this case, actually, we have only 2 pivots. So it's a column space actually is only 2-dimensional. Okay? Okay, I'm gonna stop here. 자, 그 한국말로 좀 서머라이즈 해볼게요. 제가 이제 오늘은 주로 개념을 얘기했거든요. 이제 개념이 사실 어떤 면에서 보면은 우리 학생들이 그냥 문제 푸는 거는 굉장히 잘해봤는데 사실 개념을 이야기가 상당히 어렵고요. 사실 어떤 면에 이 개념이 이게 우리 대학의 선형대수의 이제 기본을 가장 갖는 것 중에 하나를 봐요. 그래서 이제 뭐 여기 있는 사람들이 다들 우리가 문제 풀면서 그러니까 뭐 그냥 이퀘이션 그래서 n by n 이런 이퀘이션이 있다. 이걸 어떻게 푸느냐? 이건 다들 잘하거든. 박한슬이는 눈 감고도 하잖아, 그지? 눈 감고도 하잖아. 가우스 엘리미네이션, 뭐 가우스란 말을 처음 들었을 때 속어버려 다들 했잖아, 그죠? 이건 다들 잘한다고. 오케이, 잘해요. 자, 이걸 이제 매트리스 폼으로 하는 거잖아, 그죠? 그 매트리스 폼으로 뭐 가우스 엘리미네이션, no problem. 그래서 뭐 여기다 매트리스에다가 오그멘티드 뒤까지 붙여서 한꺼번에 푸는 거 no problem. 그래서 인버스 매트리스, 가우스 조단 매트리스 no problem. 그래서 여러분들이 그 알고리즘 측면은 굉장히 쉽게 이해를 한다고 하는데 이제 이걸 갖고 이제 다른 관점에서 이제 보는 건데 그래서 이걸 매트리스 관점에서 보지 않고 오늘은 상당히 이 A라는 매트릭스가 보니까 그래서 V1, V2 그래서 VN에 이렇게 그래서 각각 칼럼 벡터의 몸으로 볼 수가 있네. 예? 그래서 이거는 X1부터 XN까지 있고 이걸 리라이트 하다 보니까 X1, V1 그래서 V1은 벡터예요. 예? 그래서 이렇게 쭉 해서 XN, VN 이렇게 볼 수가 있네. 요거는 여기 벡터가 n개가 있고 그 n개의 리니어 컴비네이션 이렇게 볼 수 있잖아요. 그죠? 무슨 얘기인지 알겠죠, 그죠? 보통 이렇게 이해는 안 했잖아, 그죠? 벡터 리니어 컴비네이션 이제 그 벡터를 이렇게 리니어 컴바인 하다 보면은 요게 디멘전이 몇 개예요? 요게 디멘전이면 m 디멘전이 그지? 예? m 디멘전을 다 커버할 수도 있고 m 디멘전의 일부만 커버할 수도 있어요. 무슨 말인지 알겠어요? 컴바인 하다 보니까 이게 전부 독립적이면 다 커버할 수 있는데 독립적이지 않은 경우는 다 커버하지 않을 경우가 있거든요. 예? 그런 경우에는 일부만 커버한다고. 일부만 커버하는 게 그 subspace예요. 예? 그래서 이게 나중에 여기 밸류 이렇게 나오잖아. 이쪽에 있는 밸류가 그 subspace에 속하면은 여기 솔루션이 있는 거고. 그렇잖아요. 근데 거기 속하지 않으면 아무리 x1부터 xn의 밸류를 아무리 조정을 해도 거기 속해 있지 않은 거잖아. 그지? 그렇지 않나, 그죠? 무슨 말인지 알겠죠, 그죠? 이거 값이 없는 거지, 그죠? 솔브할 수 없는 거죠. 무슨 얘기인지 알겠죠, 그죠? 근본에 그 개념이에요. 예? 그래서 사실 이렇게 복잡한 일 자꾸 하는 거라고. 기본 그렇게 이해를 하는 게 좋다고. 지금까지 이제 여러분은 아무 이해가 없는 n equation, n unknown 풀어서 항상 one unique solution 이런 경우는 간단하다고. 예? 우리가 그렇지 않은 경우를 좀 다루려고 LS 쓰는 거거든요. 예? L 쓰다 보니까 어떤 경우에 솔루션이 존재하지? 그래서 이 벡터로 보고 벡터의 모든 컴비네이션을 봤을 때 컴비네이션을 커버하는 데 없는 것. 뭐 이렇게 생각하면 돼요. 이렇게 생각하면 된다고. 내가 전번에 이제 그 컬러 스페이스 얘기를 한번 했다고. RGB가 있잖아요, 그죠? RGB가 있다고. RGB가 프라이머리 컬러란 말이에요, 그죠? 이걸 합쳐서 모든 컬러 다 만들어낸다는 거잖아요, 그죠? 근데 하다 보니까 나는 R하고 G뿐이 없어. 그 두 개하고 컴바인하면 R하고 G1이 있구나, G2가 있어. 아니면 난 프라이머리 컬러를 나는 R하고 G하고 두 개 더한 거가 있어. 포인트를. 그래서 요거 갖고 색을 다 만들 거야. 그러면 전체 컬러 다 만들어낼 수 있나? 그 일부 컬러 만들어야잖아요, 그죠? 이게 마치 이건 3디멘셔널, 이건 마치 R3 같네, 그죠? 그렇잖아요, 그죠? 이거는 세 개인데 보니까 이게 디펜던트 하잖아, 그지? 예? 그럼 컬러 스페이스 보니까 이거는 컬러 스페이스가 디멘전이 2네? 무슨 말인지 알겠죠, 그죠? 그래서 1분만 하겠네? 이것도 보니까 이거 2네? 그래서 요게 해당되는 전체 스페이스는 거기 그걸 리프로듀스 할 수 있는데 그게 아니고 다른 데 걸 B에 다른 점이다 그러면 그걸 만들어낼 수가 없잖아, 그죠? 무슨 말인지 알겠죠, 그죠? 그렇게 해서 이해하면 편할 거예요, 개념이. 응? 무슨 말인지 알겠죠, 그죠? 그래서 전번에 이제 그림 그렸듯이 이제 컬러 스페이스가 이렇게 이렇게 모양이 돼 있으면 RGB가 3개 찍어서 사실은 이 모양은 사람 눈이 이렇게 퍼시브 하는 거거든요. 근데 여기서 이제 이거 RGB가 어디 있는지 모르겠는데 요 안에 거만 리니어 컴바인해서 만들 수 있고 이 밖에 거는 못 하지. 예? 밖에 거는 이거 하기 위해서 또 이제 점을 하나 더 찍어서 4 컬러 업셋 프린팅은 12 컬러까지 가거든요. 12개. 이제 만약에 이게 컬러 굉장히 여러 개가 있다. 12개가 있다 그러면 어떻게 되냐? 그럼 여기 점을 내가 찾고 싶거든요. 그럼 솔루션이 하나야, 여러 개야? 여러 개는 할 수 있지, 그치? 왜냐면 한번 생각해 보자. 왜냐면 우리가 이렇게 이해하는 게 훨씬 편할지 몰라. 내가 조금 전에 컬러 스페이스를 한번 공부해 보세요. 이제 사람이 퍼시브 할 수 있는 게 이만큼 우리가 인식할 수 있는 컬러야. 예? 컬러라고. 자연에서. 근데 합성을 하려면은 이 컬러를 다 합성을 못하고 합성하려면 점을 3개 찍어서 여기 3개 하면 요 3개 안에 것만 이렇게 만들어요. 이게 이제 RGB와 RGB라고. 그래서 이제 우리 형광물질 같은 걸 잘 정했다서 어떤 R은 밖에까지 하는 게 있고 어떤 R은 아, 난 그렇게 좋은 R이 없거든. 그래서 여기까지 오는 것도 그래요. 예? 실제 물질이 콤바인하면 내가 생산성 프로세스는 요것뿐이 없거든요. 그러다 보니까 이제 광고 프린터 같은 거 머신기 할 때는 여기는 컬러는 찍고 싶은데 못 찍거든. 그러면 그때는 뭘 하냐면은 점을 더 추가해. 그러면 여기 모양이 이렇게 되지, 그지? 카메라선 에리가 그죠? 더 추가해. 이렇게 된다고. 그래서 심한 건 이게 12개까지 만들어요. 좋은 프린터는. 그 12가지 만들어서 그러면 이 안에 걸 다 리프레젠트 할 수 있지. 스틸 밖에 건 안 되지만, 그죠? 그러면은 요 안에 걸 리프레젠트 하려면은 이거는 12개 컬러의 컴비네이션이라고, 그지? 근데 유니크한 컴비네이션이 있을까? 아니면 야, 이렇게 되고 저렇게 해도 여러 개가 있을까? 여러 개가 있지, 그지? 이게 마치 우리 리니어 알지브라에서 솔루션 구하려고 보니까 답이 여러 개 있네, 무한대가 있네 이렇게 될 수도 있지, 그지? 그 무한대가 그럼 그 중에 몇 개지? 그걸 다 구하고 싶은데? 그게 사실 우리가 지금 가려고 하는 방향이야. 무슨 얘기인지 알겠죠? 그래서 실제 이런 것들이 진짜 리얼 환경에 존재하는 거라고. 그래서 오늘 여기까지 끝내고 혹시 질문 있어요? 그래서 그 얘기를 하기 위해서 지금 내가 다음 시간에는 뭐 nullspace니 해서 그런 식으로 가볼게 해서 근본적으로 우리가 가려는 방향이 그러거든요. 그래서 모든 솔루션을 만들어보고 그다음에 솔루션이 없는 경우하고 이런 걸 하는 거고 그냥 우리가 옛날처럼 그냥 n 이퀘이션에 n unknown에 쉽게 풀어서 답 달랑 나오는 거 그게 아니라 그건 다른 특별한 경우에도 어떻게 할 거냐 그때 어떻게 푸는 게 좋고 그게 뭘 의미하냐 그거를 하기 위해서 뭐 벡터 스페이스니 뭐 subspace니 이런 개념을 설명한 거예요. 그리고 매트릭스가 이게 벡터의 리니어 컴비네이션이네. 칼럼 벡터에 칼럼 벡터를 리니어 컴비네이션 하다 보면 전체 커버하면은 no problem. 모든 B에 다 솔루션 있는 거고 전체 커버하지 않고 일부만 커버하면은 어떤 B 값이 거기 들어와 있지 않은 거를 풀라 그러면 못 푸는 현상이 벌어지는 거고 아까 이런 것처럼 이런 경우는 B 값이 여기 있는데 이 대면적이 더 크니까 솔루션 한 개가 아니라 무한 개가 나올 수가 있지, 그지? 이제 그 이슈를 다루는 거다. 이렇게 생각하시면 되겠어요. 혹시 질문 있어요? 오케이.